375 million years ago, a day on Earth was only about 22 hours long. The length of a day changes daily, though so minutely and irregularly that you won't really notice it. This is due largely in part to the conservation of angular momentum. The constant change in air and water masses change the distribution of matter around Earth's axis of rotation, and so the angular velocity must change with it. So you probably know about linear momentum. That's what explains why a stopped truck takes more time than a small car to reach a certain speed. And just as with energy and mass, linear momentum is always conserved. This means that if there are no external forces acting on a system, then the final amount of linear momentum is equal to the initial amount. But linear momentum only describes what is happening for objects moving in a straight line. What if the object is moving in a circle or an ellipse? Or more generally, what if it's moving at an angle? Angular momentum is analogous to linear momentum. Moment of inertia replaces mass, angular velocity replaces velocity. Instead of forces, we consider torques. If there are no external torques, angular momentum is conserved. We see the conservation of angular momentum at work every day, explaining everything from a figure skater spin to a planet's orbit. So what does this mean for physics cat? We saw earlier that an object's angular momentum is equal to its moment of inertia times its angular velocity. We can try to calculate physics cat's moment of inertia by pretending he's a cylinder, or two cylinders, or some sort of box. But to keep things simple, let's say physics cat is just one particle rotating about an axis. Let r be the position vector of our cat relative to its axis, and let p be physics cat's linear momentum. R and P are vectors, so the cross is not telling us to multiply R and P, but to take the cross prior to the 2. Thanks to some clever mathematicians, we know that if we cross a mountain climber with a mosquito, we don't get anything, but if we cross an elephant with a mouse, we get elephant mouse sine theta. So let's cross R and P to get RP sine theta. We know that P equals mv, so we plug that into our equation. If our cat's distance, mass, or velocity increases, its angular momentum increases as well. Changing physics cat's direction changes the sign of L. What if physics cat is moving with constant speed? This is called uniform circular motion, which lies at the heart of all the ball and string problems you see in physics classes. Of course, there are all sorts of interesting applications of uniform circular motion, but physics cat wants to end on a cool example of angular momentum you might not have thought about before. Consider a black hole. Because angular momentum is conserved, if a star is rotating when it collapses, then the black hole that is formed will also rotate. As a result, the black hole will distort space and time, and if a particle gets close, it will start rotating too. This is called frame dragging, or the lens-tethering effect, and is related to Einstein's general theory of relativity. But very simply, the rotation of a massive object distorts space-time, causing any nearby particles to rotate as well. Fortunately, though, the lens-tethering effect is very small, and thanks to angular momentum, physics cat can rest easy tonight.